Right, so today we were looking at a paper called XPRL, Exploratory RL for LLM Mid-Training. It's by Violet Chang and a whole team from Stanford, CMU, OpenAI, and Rogo.
Yeah, a really heavy-hitting lineup for this one.
Seriously. And if you're trying to scale reasoning in AI right now, sparse-reward reinforcement learning is, it's the absolute gold standard, but it has this fatal flaw.
Right, the exploration bottleneck.
Exactly. If your base model just natively cannot spontaneously generate a correct answer to some brutally hard math problem, those sparse rewards give you zero learning signal. The policy just kind of thrashes in the dark.
It's totally blind.
Right. So this paper solves that bottleneck by introducing XPRL for a mid-training phase. Instead of forcing a model to blindly imitate human reference solutions, which actually completely disrupts its native reasoning, XPRL uses those references secretly.
Yeah, that's the genius part. An LLM judge looks at the human reference and gives the training policy these dense rewards for partial progress.
Which perfectly primes the model for your downstream sparse reward RL later. So, welcome to AI Paper Slop. Our mission for you today, whether you're, an ML engineer tuning a pipeline or a researcher tracking scaling laws, is understanding how to build what this paper calls coverage.
Coverage over productive reasoning paths, specifically.
Right, and doing it before you burn massive amounts of compute on stage 2 RL. Think about it like throwing a student into this advanced, completely unsolved calculus exam, and you only grade the final box answer at the very bottom.
And if it's wrong, you just hand the paper back with a big red 0.
Exactly. No feedback, no notes. That is literally what we are doing to large language models right now with standard sparse reward RL. XPRL, by contrast, is like a teacher giving partial credit.
Right, giving credit for showing the correct logical steps, even if that final calculation at the bottom of the page is, completely botched.
Yeah, the calculus analogy really strikes at the heart of the limitation we face with algorithms like GRPO on these incredibly hard data sets.
It really does. And just for the listeners tuning in who might not be deep in the reinforcement learning trenches every single day, GRPO, or Group Relative Policy Optimization, is basically the current state of the art for rewarding a model.
It's everywhere right now.
Yeah, it works by having the model generate a whole batch of different answers to the same prompt. Then it scores them and uses the mean and variance of those scores to calculate an advantage. So the model learns by essentially comparing its own attempts against each other.
And here is the massive catch. The underlying assumption of GRPO is that at least some of those attempts in the batch actually hit the target.
Right, so you see the problem. If we look at the baseline setup in this study, I think they used the Quen 3.4b instruct model, and you feed it a highly complex competition math problem. The chance of it getting the correct final answer on the first try.
Pass at one rate.
Right, its pass at one rate might be mathematically indistinguishable from 0. It's just too hard. If the model natively does not assign any probability mass to the productive reasoning paths required to solve that specific problem, you're entirely stuck.
You could sample the model 64 times or 100 times and just get 0 successes.
Exactly. You get nothing.
So the batch of answers generated for GRPO to compare are really just like 64 different variations of being completely wrong.
And in that regime, giving a sparse final answer reward of 0 to every single rollout provides absolutely no gradient signal. The model learns nothing.
Worse, right?
Yeah, even more dangerously, if the model accidentally stumbles into the right answer through a complete fluke, say, 2 catastrophic math errors just happen to cancel each other out, the RL algorithm will just reinforce whatever idiosyncratic, flawed logic the model used to get there.
Proxy hacking the math.
Exactly. It does not learn the generalizable skill of solving the problem. It just learns how to exploit the reward function. Therefore, the objective of this mid-training phase isn't actually to push the pass at one metric to 100% immediately.
Right.
The objective is to increase pass at k.
Meaning, if we sample the model k times, we want to mathematically guarantee that it consistently explores viable, logical solution paths in at least a few of those rollouts.
You're aiming for a baseline level of competency. You want to ensure the neural network places at least a fraction of its probability mass on the correct broad strategies.
Because once you establish that coverage, your downstream sparse reward RL finally has a meaningful signal to grab onto and optimize.
Exactly. It gives GRPO something real to work with.
Okay, but I can already hear the friction from the practitioners listening to this right now. Because if we already possess this highly curated data set of brutal math questions.
Mid-training data set, yeah.
Right, and we have perfect human-written reference answers for all of them. Why on earth Are we introducing the immense overhead of reinforcement learning?
It sounds overly complicated, I know.
Like, why not just run supervised fine-tuning, or SFT, and force the model to imitate the human text? We literally have the answers. Just inject them into the weights.
Well, the researchers actually anticipated that exact pushback, which is why they ran exhaustive baselines comparing their method against SFT and self-distillation.
And the data is pretty shocking, honestly.
It is deeply counterintuitive until you look at the underlying math. SFT and self-distillation catastrophically fail here.
Wow. Catastrophically.
Yes, because human reasoning traces rely on cognitive strategies, intuitive leaps, and structural approaches that are fundamentally foreign to the base model's internal representations.
It's kind of like trying to memorize a chess grandmaster's moves without actually understanding the board state or the overarching strategy.
That's a perfect way to look at it.
You might confidently play the first 3 opening moves perfectly from memory. But as soon as the opponent plays a variation you haven't memorized, you end up making illegal moves because you don't actually know why your pieces are positioned there.
Right. The chess grandmaster analogy perfectly maps to the concept of KL divergence, which the paper measures explicitly during self-distillation.
Okay, break that down for a second. For context, self-distillation is a technique where you condition the base model on the correct reference solution, have it generate a trace, and then use that as a teacher to train a student version of the model.
Right. And the researchers proved that the target distribution of that teacher starts way, way too far outside the KL ball of policies that are organically reachable by the student model.
Wait, unpack that concept of the KL ball for us. What does that actually look like inside the network?
Think of the KL ball as the safe radius of probability space where the model can update its weights without completely breaking its existing knowledge.
Like a safety zone.
Exactly. It's the space of policies reachable by small, stable gradient steps. When you force the network's weights to update aggressively toward a highly specific human-like solution path that the model's internal map considers impossible or highly improbable, you trigger violent, unstable optimization.
You're literally tearing apart its generalized reasoning capabilities just to force it to memorize one incredibly narrow path.
Yes, SFT and distillation create a severe off-policy mismatch.
So we are caught in this massive paradox. We have these perfect human reference solutions, but we just established that showing them directly to the model for imitation effectively destroys its generalized reasoning.
Which brings us to the core problem.
Right. So how does the XPRL architecture actually leverage this data without ruining the model?
This is where the methodology gets truly brilliant. XPRL utilizes the human reference solutions strictly as secret reward scaffolds.
Secret scaffolds. I love that.
The policy model that's actively being trained never actually sees the human text. It is only fed the problem prompt, and it is forced to generate an on-policy rollout.
So it attempts to solve the problem, utilizing its own native logic, its own token distribution, and its own preferred formatting.
It is entirely exploring on its own, completely blind to the answer key.
Then the framework introduces a separate LLM judge. In this specific study, they used an identical frozen Qwen34B instruct model.
Right, and the judge is the only entity that has access to the hidden human reference solution. The judge is tasked with using that reference to construct a highly rigorous grading rubric on a 1 to 5 Likert scale.
And the criteria for that Likert scale is based on logical alignment rather than exact text matching, right? Because we don't want it just checking if the words are the same.
Exactly. The prompt given to the judge explicitly instructs it not to solve the problem itself and definitely not to infer any missing logical steps.
It just grades the math.
It simply evaluates the policy's raw output and asks, is this mathematical reduction sound? Does it align with the necessary intermediate claims established in the human reference? Does it contradict anything we know to be true?
And based on that purely logical evaluation, it assigns a dense reward. Now, the paper tests 2 distinct variants of this setup, right? XPRL outcome and XPRL process.
Right. So XPRL outcome operates as the broader approach. It allows the policy to generate the entire complete rollout from start to finish, and then the judge issues a dense terminal reward at the very end based on that 1 to 5 rubric.
This means that even if the policy completely fumbles the final arithmetic and gets the answer wrong, if the reasoning steps leading up to that error were, say, a 4 out of 5 on the Likert scale because it correctly set up the casework,
the model still receives a strong positive reward.
which is a massive paradigm shift. Because under a standard GRPO pipeline, that exact same rollout gets a hard 0.
It's a total game changer. And then the alternative variant, XPRL process, takes this a step further into granular optimization. It takes the policy's complete rollout and actively slices it into intermediate prefixes.
Oh, right. It leverages the ### delimiter that the Quinn-based model naturally outputs to separate its reasoning steps, doesn't it?
Yeah.
It just slices the text every time it sees that marker.
Exactly. And the judge scores every single one of those distinct segments individually. This provides highly localized credit to specific moments of partial progress.
Wow.
Yeah, the researchers are explicitly weaponizing what we call the verification generation gap.
The idea that models are better at checking work than doing work.
Yes. We know definitively that current LLMs are significantly more capable at verifying partial progress against a known factual reference than they are at generating a complex solution from scratch.
Makes sense.
By constraining the judge to verification rather than generation, the framework extracts an incredibly high-quality, dense reward signal out of a relatively small 4 billion parameter judge model.
Now, with the process variant, I noticed they do something very specific with the advantage centering math. They aren't just directly feeding those absolute 1 to 5 Likert scores back to the policy to optimize against, are they?
No, and that mathematical adjustment is really the secret sauce for isolating localized credit. Instead of using the raw score, the algorithm calculates the advantage by subtracting the previous step score from the current step score.
So just to map that out for everyone, if step 2 of the model's reasoning receives a score of 3, and step 3 advances the logic and receives a score of 4, the advantage assigned to step 3 is a positive 1.
Right.
But if the model goes from a 4 down to a 2, the advantage becomes deeply negative.
Exactly. By framing the advantage as a delta between steps, the model only receives a positive gradient update if it actively improves its alignment with the human reference.
That is so smart.
This mathematical constraint forces the policy to continuously build on its intermediate progress, rather than finding one decent early step, receiving a high score, and then just coasting with generic lazy output. It actively punishes logical regression.
So the logic holds up beautifully in theory. You use hidden references as secret rubrics to provide dense rewards for localized on-policy exploration. But, theory doesn't pay the compute bills. Did this dense reward structure actually survive contact with the AIM benchmarks?
The empirical data is just overwhelming here. The researchers structured this as a 2-stage training pipeline. Stage 1 is the XPRL mid-training phase, and they only ran it for 230 optimization steps.
230, that is a remarkably short priming window.
It really is. Stage 2 is then standard sparse-reward GRPO for 500 steps, running with absolutely no references provided. And they evaluated the final models on held-out, exceptionally rigorous math benchmarks.
Let's look at the AIME 2026 data specifically, because AIME is notorious for completely breaking models.
Oh, absolutely. Well, the model initialized with the XPRL process variant reached a massive 63.41% pass at 1 after the downstream GRPO stage.
63.41%. And how did the baselines perform under the exact same stage 2 RL conditions?
Standard GRPO with no XPRL mid-training priming at all peaked at 58.75%.
Okay, a decent gap.
But the supervised fine-tuning baseline, where they tried to just force the model to imitate the references, that plummeted to 30.26%.
Wow. Forcing the model into SFT completely tanked its ability to survive and learn from stage 2 RL.
The off-policy mismatch just destroyed its capacity to explore later.
And we see this dominance repeated across other data sets too, right?
Yeah, on the HMMT benchmark, which tests highly complex multi-step theorem proving, and the IMO answer bench, which is drawn from the International Mathematical Olympiad. The XPRL variants consistently dominated the top of the performance tables.
So the gap wasn't just a statistical margin of error, it was a fundamental capability shift.
Exactly.
So for the ML engineers listening right now and thinking about their own training pipelines, the major takeaway here is that the XPRL initialization fundamentally shifted the pass at K probability distributions before stage 2 even began.
It set the stage perfectly.
By consistently rewarding partial progress, it pushed the network's probability mass heavily toward productive reasoning trajectories. So when the downstream GRPO finally kicked in, the model was already exploring the correct neighborhoods of the solution space.
GRPO wasn't blindly stumbling in the dark anymore. It actually had coverage.
Right. Now, the aggregate metrics prove it works, but the paper actually goes a step further to analyze the specific tokens the model was outputting. They wanted to know how the model's cognitive behavior changed to achieve those scores.
This part of the methodology was fascinating. They didn't just measure the final mathematical accuracy, they brought in Claude Sonnet 4 as an independent external annotator to read the model's rollouts.
And they classified the text based on a strict behavioral rubric.
Yeah, they instructed Claude to scan for solution archetypes like coordinatization or casework, but more importantly, to measure process behaviors. The analysis revealed that models primed with XPRL showed massive net gains in search-oriented cognitive behaviors.
What kind of behavior specifically?
We are talking about instances of verification where the model actively plugs a derived answer back into the original equation to test it, as well as self-correction, and intentional backtracking when a logical path hits a dead end.
So the model independently learned to double-check its own work and pivot if the math didn't add up.
And conversely, the models forced through the SFT imitation pipeline exhibited a catastrophic loss of those exact verification behaviors.
Because when you force a neural network to memorize a specific text sequence, it stops actively checking its internal logic. It just recites the memorized pattern.
Right, it just repeats what it was told.
I do have to push back here, though. Based on a deep dive into the behavior charts provided in the paper, the data clearly shows that the self-distillation baseline also increased self-correction and exploration behaviors.
It did, yes.
In fact, on a few specific behavioral metrics, self-distillation increased those search behaviors even more than XPRL. So if self-distillation was successfully teaching the model to explore and self-correct, why did its performance on the actual AIM benchmarks collapse so dramatically?
That tension in the data reveals the most crucial nuance of the entire paper. Behavioral coverage in a vacuum is basically useless.
How so?
It is not enough to simply teach a model how to backtrack or how to self-correct as an abstract concept. You need search behaviors that effectively scale test time compute, combined with coverage over problem-specific, productive solution paths.
Oh, I see. So self-distillation was teaching the model the mechanics of guessing and checking, but because the target distribution was so deeply off policy, the model was guessing and checking in entirely the wrong neighborhood of the mathematical solution space.
Precisely. You can be the greatest maze runner in the world, exceptionally skilled at backtracking when you hit a wall, but if you are dropped into the completely wrong maze, your backtracking skills will not help you find the exit.
That makes a lot of sense.
XPRL achieves both requirements simultaneously. It natively encourages the search behaviors, but the dense reward scaffold provided by the secret rubric ensures those search behaviors are actually anchored to the human reference path. It aligns the model's exploration with mathematical reality.
That distinction really clears things up. Now let's test the boundaries of this methodology. Does this dense reward structure only work for a 4 billion parameter model solving high school competition math, or does it generalize?
The researchers intentionally ran a mixed domain scale study to test exactly those boundaries. They scaled the policy model up to an 8 billion parameter architecture, but crucially, they maintained the smaller 4 billion parameter model as the judge.
Which is incredible news for anyone managing compute budgets. You don't need to deploy a massive 8B judge to evaluate an 8B policy.
Because the judge has access to the hidden reference solution, the evaluation becomes a highly scaffolded verification task. A smaller 4 billion parameter model is perfectly capable of verifying logic against an answer key.
Right.
They trained this scaled-up 8B policy on a highly diverse mixed domain: math, a science QA dataset they call Sino, and a coding dataset using Live Code Bench.
Did the performance hold up across the board?
XPRL outcomes successfully improved the 8B base policy across all the math and Sino aggregates. It proved definitively that reference-guided RL priming isn't just teaching the model rigid, math-specific formatting templates.
It's actually building cognitive coverage across a much broader mixture of generalized scientific reasoning.
Exactly. But the paper explicitly notes a massive caveat in the coding domain.
Right, the coding dataset. The framework completely failed to beat standard sparse GRPO on the Live Code Bench dataset, didn't it?
It did. It totally fell flat.
Why did the code completely fall apart?
It comes down to the fundamental nature of the reward structure in computer science. Coding provides an incredibly strong, perfectly calibrated sparse reward mechanism, naturally the compiler.
Right, the execution environment.
The code either compiles and passes the unit tests, or it fails. There's no ambiguity. Furthermore, asking an LLM judge to evaluate partial code against a reference solution is an inherently subjective and flawed task.
Because there are, thousands of valid ways to structure a function or define a variable.
Exactly. A model might write a brilliantly optimized, highly unconventional loop that looks absolutely nothing like the human reference code.
Right.
If the LLM judge is forced to score your partial code against a fundamentally different architectural approach in the reference, it is going to heavily penalize the rollout, even if that code would eventually compile perfectly and solve the problem.
It seems like mathematical reasoning is fundamentally akin to writing a persuasive essay. The intermediate arguments matter deeply to the judge. The logical flow has to be structurally sound at every single step to reach a valid conclusion.
That's a great comparison.
But coding is like building a bridge. Either the car drives over it without collapsing into the river, or it doesn't. You don't need an LLM judge to meticulously grade your blueprints on a Likert scale if you have the laws of physics or a compiler to test it instantly and flawlessly.
That distinction really dictates where this framework should be deployed. When an absolute strong environment reward is available, downstream RL should rely on it directly.
Right, skip the mid-training overhead.
Yes. XPRL is specifically engineered for domains where intermediate logical reductions must be compared against a known path because the final outcome is simply too sparse for the model to reach blindly.
Okay, before we wrap up, we need to dive into the ablation studies, the messy engineering realities that the ML practitioners listening to this need to anticipate, because deploying these architectures is never just plug and play.
No, the implementation details always expose the real limitations of the framework. The researchers ran a highly revealing misplacement rate test to check the actual calibration of the judge model.
Oh, this was fascinating.
The core question was, is the 4B judge actually utilizing the human reference scaffolding to assign accurate logical rewards, or is it just hallucinating and assigning high scores to any text that looks confident and mathematically plausible?
The classic LLM sycophancy trap.
Exactly. To test this, they deliberately fed the 4B judge the wrong human reference solution for a given problem and asked it to score a rollout.
And what happened?
Under those conditions, the judge's ability to assign accurate, correlated rewards completely collapsed. Its misplacement rate skyrocketed.
Which, paradoxically, is exactly what you want to see.
It proves the system is genuinely relying on the reference scaffolding to verify the math, not just defaulting to generic LLM confidence heuristics.
That's a relief.
Although it is critical to note that when they attempted this entire setup using a tiny 0.6b parameter model as the judge, the optimization became completely unstable. You absolutely need a minimally capable reasoning model for the XPRL framework to function.
Good to know. Now, there was one other implementation quirk in the paper that perfectly highlights the dangers of RL constraints.
Oh, the collapse of the hash delimiters.
Yes. During the XPRL process training phase, where the model is actively scored on every single step it takes, the researchers noticed that the frequency of the hash delimiters in the model's output suddenly plummeted.
It just dropped off a cliff.
The model actively stopped breaking its thoughts into granular steps. Why did the model suddenly refuse to show its work?
It wasn't a failure of the XPRL algorithm itself. It was actually caused by the length clipping penalties interacting disastrously with the process-level rewards.
Okay, explain that.
In standard RLHF and GRPO pipelines, engineers implement severe length penalties to prevent the model from infinitely generating reasoning tokens to farm reward or just burn compute.
So the model realized that if it output fewer step delimiters, it would technically generate fewer distinct segments.
Exactly. By skipping steps and compressing its logic into giant merged blocks of text, it found a highly efficient, lazy workaround to avoid the length penalties while still technically arriving at the final answer.
It is the ultimate cautionary tale for reinforcement learning alignment. The neural network will always optimize ruthlessly for the exact mathematical constraints you provide, even if it completely breaks the semantic structure you intended to encourage.
You will always find the shortcut. Always.
It's a fantastic warning for the engineers listening. Always monitor your token distributions. Don't just celebrate the final reward graph going up. If your step delimiters suddenly disappear, your model isn't getting smarter. It is proxy hacking your constraint gradients.
And that requires constant vigilance during the mid-training phase.
Putting this all together, XPRL represents a fundamental shift in how we prime LLMs for complex reasoning. Instead of the rigid, imitate this exact path philosophy of SFT, XPRL proposes a framework of explore your own path, and I will mathematically signal if you are getting warmer.
It provides localized partial credit to guide the model's probability mass into the correct neighborhood, ensuring that algorithms like GRPO can actually execute their optimization effectively.
It comprehensively solves the exploration bottleneck by transforming static human data into a dynamic, dense reward scaffold. But analyzing this architecture leaves me with one massive provocative thought, and this is what I want you, the listener, to mull over on your own today.
Let's hear it.
This entire XPRL methodology is undeniably brilliant, but it relies entirely on the existence of human-written reference solutions to act as the hidden rubric. It fundamentally requires a teacher holding an answer key.
Right.
But what happens when we push LLMs to solve truly novel frontier problems, unproven mathematical theorems, zero-day security vulnerabilities, complex scientific discoveries where no human reference exists anywhere in the world?
That is the big question.
Can we engineer models capable of generating their own mathematically sound XPRL rubrics through self-play? Or does the exploration bottleneck inevitably catch up with us at the bleeding edge of human knowledge? If the teacher doesn't have the answer key to construct the rubric, how does the student learn to explore?
It's a fascinating problem.
Think deeply about that constraint. Thank you for joining this breakdown on AI Paperslop. Be sure to read the full methodology via the link in the description. We'll catch you on the next deep dive.